Second lecture in Module 6, we're talking very brief overview of semantic analysis. And we discussed that semantic analysis is trying to provide some insight into program meaning, and the meaning that's a very limited amount of results that we can obtain based on the church Turing thesis, that you cannot take a program, give it to another program, and get a complete analysis on things like will it halt, or will it do this, will it do that. But we can do some things like, we talked largely about type checking. You can also start to ask questions about the state of memory. Is every variable properly defined at any point in time? These kinds of things. So, the three major forms, denotational, operational, and axiomatic. And I'll talk about each one in turn. So what denotational talks about, it treats the semantics as a mathematical expression, and I mean that in the most formal sense. This is the kind of, all three of these are used in proof techniques, but this seems to be, I won't say that. All three of these are used for proof techniques, so they're all formalisms. But denotational is very notationally dense, but it frames things in a mathematical format, truly computational mathematic. The denotational semantics that I've seen actually rely on the lambda calculus, which we're going to study next after this section. Unfortunately, I can't go into the future and use that and bring it back right now, but that's the format. The idea of the memory in a computer is abstracted away to a program store. A program store is nothing more than a set, and I mean that in the mathematical sense, a set of variable value pairs. And the meaning of the program, again, observable input-output behavior, is to take an input store and transform it to an output store. So if I wanted to ask the questions, are these two programs equivalent, I could answer that by saying, well, for all possible input stores, here's the set of all possible input stores, we get the same output store. Then in terms of behavior, those two programs are equivalent. Hopefully it makes sense to you. Only assignment statements can change the store. Loops are statements that may contain assignment statements, right? But the loop itself doesn't change the store. It's the assignment statements inside the loop that change the store. And the same with if then else. It doesn't change the store. It's the assignment statements inside the true and false branches that change the store. And then once you have the idea for what an individual statement does, and we only need to worry about declarations, which add entities to the store, assignments, which change the variable value pairs in the store, if then else's and loops, which in and of themselves don't change the store, but the contents of their bodies will. Then the only thing we have to worry about is I/O, and we don't worry about I/O here. We're purely focused on computation. But so once you have those statements, then you say, okay, that's great. I know I have rules for the statement, but what about rules for a program? Well, a program is a sequence of statements. So we need a rule for how sequences of statements work. And so if you say, okay, I have two statements, S1 and S2, what's the rule for that? Well, I evaluate S2 based on the store that S1 gave me. So basically, I have an initial store, S1 does something, now I have a new store. Now S2 takes that new store, evaluates it, and creates another store. And if I had an S3, it would take that store. So what we're dealing with is the notion that statements are atomic. This is actually important in the context of a compiler because remember I said right up front, what does the compiler do? It rips your program all apart. Oh, and by the way, it also may take what you think is one statement and turn that into 3 or 4 or 10 mini statements. Well, what we have to do is make sure that what the compiler has to do is make sure that the mini statements from S1 all need to be completed before you start any of those mini statements from S2. Or if they're interleaved, some of the statements from S1 aren't done, but some of the little mini statements from S2 do start. That can only be done if the compiler can prove mathematically that the actual overall input-output behavior hasn't changed if you did all of S1 and if you did all of S2. Why would they do that, though? Why would they do start doing some of the mini statements from S2 before S1 is done? That has to do with making sure that you are using your cache memory most efficiently, that you are using the registers in the chip most efficiently. And so they want to do that to take advantage of those efficiencies, but the rule is you can't change the outcome. You have to make this act as if S1 executed and then S2 executed. So this is a place where these semantic formalisms can formally prove that a particular optimization will not change the result. Because you can do anything you want for optimization as long as you don't change the result. And we have formal ways to do that. Okay, so for example, for denotational, if you're given some program store, and we use sigma for program store, variable 1 value, variable 2 value, variable 3 value, and then you have this term eval x sigma. In other words, evaluate the x variable given the current store. What that does, it just goes in and finds x and then looks for the current value associated with it. But we can do that with expressions too. Evaluate an entire expression based on the current store. Well, what's an expression? Let's say it's x plus y. Okay, you have to go into the current store, find the value of x, go in the current store, find the value of y, and then x plus y. This is why in Java with our other programming languages, I++ and ++ I, it's kind of odd, right? So if I said instead of x plus y, I said ++ x plus y. Whoa, that's actually two statements. ++ x says increment x before you do the plus y. So we're actually modifying the store. So really that gets broken up into, okay, find the current value of x and increment it. Now you've got a new store. Take the current value of x in the new store plus the current value of y in the new store, add them together. So now if we take these two things and say x equals expression, we have a way to denotationally represent that. What are we going to do? Just in general terms here, what are we doing? Well, if x equals expression, let's see. Just notionally, what are we doing? Well, we're going to evaluate the expression using the current store, and then we're going to find where the current store x value pair is, remove that, and replace it with the new x value where the value is whatever this expression was. That's what it does notionally. So then we can say that a little more formally. Oh, x equals expression. What's the semantic meaning of that? It means take the current store, subtract out the current x value, and union it with x, evaluate the expression using the current store. So initially we say, okay, current store, x is undefined and y is undefined. Why is that? We've declared x and y, but we have not given it a value. Then we say x equals 10, so we remove x undefined and we add x10 to the store. Then we say y equals x times 2, evaluate x times 2 based on the current store. And so we replace y undefined with y, evaluate x times 2 with the current store. And so now our current store is x10, y20, and you can go through and do this for every line in the program. Now, again, what people don't tend to do is actually do this operation. What people do is define these things, and then they can make formal proofs about the effects of program operations, or program optimizations, or the effect of moving a statement around, or the effect of running a program. So you can make formal proofs that current optimizations, that optimizations don't actually change the result of the input-output behavior of the program. This becomes much more complicated in a parallel processing world, and nowadays we all live in a parallel processing world because even most laptops have multiple processors in them. But these are the kinds of tools that people use to make sure that those processors work efficiently and don't mess up your programs. Okay, operational semantics is based focused more on the behavior or the operations of a machine, the operations of a system. And there are different forms of operational semantics. A popular form is based on formatted in the same way that we did logic in the discrete structures class. So we have if P1 and P2 and P3 then Q, that kind of thing. Oh, and that tends to be written this way. This is a fairly common way to write these in both the semantic analysis world and in the logical world. Premises on top, anded together, vertical line, result on the bottom. P1 and P2 and P3, therefore Q. And the idea is if you meet conditions P1 and P2 and P3, then Q is valid. And how does this look? And I'm not going to go through too much detail, but I know this surprised you, didn't it? But what's happening here is this is a mini language called Wren, which the authors of the Pelican book use as their sample programming language. And they've created an operational semantics for these things. You start out with the basic numbers. N is from the set of numbers, and it's an integer expression. An ID is the set of allowable IDs or variable names, also an integer expression. B is a Boolean expression, and it can only be true or false. And BID is a Boolean variable, and it's from the allowable names for a Boolean variable. And then you say if you have if BE1 is a Boolean expression and BE2 is a Boolean expression, then BE1 Boolean operator BE2 is also a Boolean expression. If BE is a Boolean expression, then not BE is also a Boolean expression. You can see they're going to do some kind of typing and type analysis here. And all these things. If C1 is a command and C2 is a command, command is what they use for statements here. If C1 is a command and C2 is a command, then C1 semicolon C2 is also a command. In other words, that's how you make programs, one statement after another. If IE is an integer expression, then this is assignment. If IE is an integer expression and ID is in the set of all possible IDs, then ID equals IE is a command. That's the assignment command. This is the if-then-else command. I'm sorry, that's the if-then command. That's the if-then-else command. That's the while command. They don't do for because remember, for and while loops are actually equivalent to each other. So that's all the rules in terms of typing. And then they can verify that this is not just a syntactically correct statement, but it is a semantically correct statement because the typing works out. If you say x equals 5 and then you say while not x equals 0, do x equals x minus 1, write x, they're saying that's a command. Remember, sequences of statements are a command. And they're saying that's a command. And then they want to prove it. It's a type analysis exercise. They want to prove that. So they break it apart and break it apart and break it apart. First they break apart this x equals 5. Well, sure enough, we have a rule for that. If we have an integer expression and we have assignment, x equals 5, then that's a command. So that's a legal command. And then they do the while in the right, and they break out the while and they break out the right. And they do the same thing over and over. I'm not going to walk through this because I'll do it in the live lecture in more detail. But what they end up with is they say, wow, that x equals 5 is a legal command, and the while not x equals 0, do x equals x minus 1 is a legal command, and write x is a legal command. And using this rule that sequences of commands are commands, they can do a type analysis to verify that the whole thing is semantically correct. And then the last form, I told you this was a top overview, right? By the way, those of you, again, if you take SE410, you almost certainly will see this format again, but in the context of systems and the, you're going to spend more than 5 minutes on how to use it. Axiomatic analyses. Well, axiomatic semantics describes the program in terms of sets of axioms or sets of true statements. What do we know to be true about the program at any point in time? And the general form of this is you have a set of statements that are true before a statement executes, and then you execute the statement, and then you have a set of things that are true after. So you have a preconditions, execute, post conditions. By the way, this is actually used in UML diagrams and in some program design settings where you're saying, okay, I want to do a test case. What are my preconditions? Then I run the test. What are my post conditions? Or you're saying, I'm going to run a method. What are my preconditions? Then I run the method. What are my post conditions? So this actually does bleed over into software design documents. And it's pretty straightforward. You know, the things that you're saying are true can be anything. Has X been declared? Has X been initialized? Is X a legal variable name? The value of X is equal to 12. Is, you know, true or false? So almost anything that you can think of in terms of a true-false framing, you can write the precondition for and say, okay, we know these things to be true now. When you start out, you have an empty set, right? When nothing is true, and then you start to do declarations and you start to do statements. And as you do each one, you just add to the list. Okay, now this is true, now this is true, now this is true. If you had something like x equals 12 is in your set of conditions, and then you change that to x equals 32, obviously you have to remove x equals 12 and add in x equals 32 as your list of axioms. So these are the three basic forms. I'm covering them super briefly, but denotational, operational. Denotational is, again, is focused on mathematical modeling of the computation. Operational is focused more on the operations of the program, or actually the operations of the machine. So some operational semantics will go into the hardware. And then axiomatic is about what do we know to be true about the program at any point in time. And we'll go over these again in the live lecture.